Hello, everyone. I'm making this new recording of the two portfolios, reviewing the two portfolios because the one I had saved from last year for some reason is not showing the video on it, so which kind of defeats the purpose of it. So this Unit 3 review live lesson recording or lesson recording is for you to review the problems from the two portfolios at the end of Unit 2. So for Unit 3, Portfolio 1, your first task was to take the statement here that says the month of January has 31 days and write the type of statement based on the original statement, which means a conditional statement we have to write an if-then statement. That kind of goes in the same order as what we see up there. We should be mentioning the month being January and then it having 31 days being the conclusion. Um, Converse, inverse, and contrapositive are all if-then statements too, but they're basically manipulations of the conditional statement. The thing that you have to make sure that you're doing is when um, you're creating these if-then statements, the if statement, the hypothesis part, must be something that can possibly be true when you're doing this. And so, for instance, I've seen students in the past make an error on this question, and it doesn't seem like an error at first, but when they go through it, I mean, for instance, they'll say, if January is a month, then it has 31 days. Not necessarily a wrong statement, kind of clumsily stated, but there is an issue with this as we go along with this. So if I go to the converse, if January has 31 days, then it is a month. Again, there's still some rudimentary issues with this because when you get to the inverse, if January is not a month, then it does not have 31 days. And that's where we're going to have an issue with this. If January is not a month, then what is it? Aside from maybe, I think I may have heard of one person or two people named January out there. You don't usually see that very frequently. So, if you're mentioning the word January, it's, rest assured you're probably talking about the month. So for you to say if January is not a month, you're assuming something that could not possibly be true, and therefore that's where this kind of breaks down. So this is not really, these are really not, so the original conditional statement is not really good because when you eventually get to the converse and inverse and all these things, the statements you're sometimes making, if January does not have 31 days, then it is not a month. Again, assuming that January does not have 31 days, well, it does. There's only one month out of the year that fluctuates in number of days, and that only does every 4 years, and that's February. All the other days have a set number of days to them. I said all the other months. Um, some of these if statements and these conclusions, you know, are impossible to happen. So when we make the conditional statement, it has to have at least an if statement, as we go through all of these that can assumed to be true. So this is not a good way of stating it. Then you'd have issues with, trying to determine the truthfulness or falsehood as we go along and answer the rest of the questions. Um, so that's what this is kind of getting at. So these are the wrong answers. This is usually how I can sometimes tell if students are paying attention to this recording, because I'll have students that'll write these down because it's the first answers they see, and meanwhile they're not listening to find out that these are the wrong answers, and that's what they give me on the when they turn in their portfolios. The correct answer or better answers for these four are as follows. The conditional statement is if the month is January. So months could be different. I could have a different month. I can't have different Januaries, or I can't have January be a month and then not be a month. So if the month is January, then it has 31 days. And if I go through the rest of them, of course, when I do the converse, just switching the if and then part. If the month has 31 days, then it is January. The inverse, if the month is not January, then it does not have 31 days. And if the contrapositive would be if the month does not have 31 days, then it is not January. And each one of these, the if statements can be true. Uh, you know, The month can be January. A month can have 31 days. A month cannot be, is also possible not to be January. It's also possible for a month not to have 31 days. So each of those if statements can, in fact, be true. So, you know, that's one of the things you have to kind of look for as you go through and make these conditionals. The original conditional statement is that when you do these other ones, does it make sense? Do these make sense as well? So even when you have a question that doesn't ask you about the converse, inverse, and contrapositive, you should be considering them nonetheless so that you can make sure that the conditional statement that you came up with is worded as well as it possibly can be. Because if it's not worded the right way and you do some of these other ones, you might get an if statement that can't happen, and the whole thing breaks down as far as the ability to say it's a good conditional statement. So based on the responses above, what are the truth values for each? Well, if the month is January, then it does have 31 days. That is true. There's no doubt about that. However, if the month has 31 days, then it is January. Well, that's false, because there are other months that have 31 days in it. October, December, just to name a couple. Um, Therefore, the inverse, if the month is not January, then it does not have 31 days. Well, again, a month that's not January would be like July. July does have 31 days, so it makes this statement false. And the other thing you have to keep in mind is that the converse and the inverse are logically equivalent. They should have the same, truth value. Just like the contrapositive and the original conditional statement, they're logically equivalent. So if the month does not have 31 days, then it is not January. So if I pick any day, any month that does not have 31 days in it, none of them are going to be January. So that is a true statement. So write the biconditional statement for the original statement, and is the biconditional true? So here again, I'm kind of patterned after the conditional statement, but remember we used the phrase if and only if. So a good way of stating that sentence as a biconditional statement is the month is January if and only if it has 31 days. Because you still want to keep the same general order as it originally was. Is it a true statement? Well, you have to remember that a biconditional statement is the combination of a conditional statement and its converse. So this is only true if, I could break this into a conditional statement and the converse of that conditional statement and have both of those be true. And as you can see above, that's not the case. A lot of people think like, well, January does have 31 days, so it's a true statement. But you also have to say, okay, this is also saying if the month has 31 days, then it is January. That's what if and only if is implying, and that's not true. So for that reason, because whichever which way you look at it, this is a false statement. The biconditional is false. And so one of the last questions you usually ask is the original statement a good definition? In geometry and mathematics, a good definition means that it can be written as a true biconditional statement. So in part C, when we said it wasn't a true biconditional statement, that means that it's not a good definition either. So some of these questions are kind of asking the same thing, and that's where some students have difficulties. They don't realize it because they have not, played around with these enough to know that. So make sure that you know when sometimes questions are being asked of you, or the same questions asked in a different way. So in this one, we're being asked to write a good definition of a linear pair. And we want to be able to write that definition as a biconditional statement. So we should be able to write a biconditional statement that's true, because it makes it a good definition. So a linear pair occurs when I have two angles that share a vertex, and basically together, I start from one angle, move to the terminal ray of the other, which will be an initial ray of the second one, and then go through that angle that combined, they form a straight angle or a line. So essentially, I could look at a linear pair being angles that are adjacent to each other because they do share a side. Excuse me. and they have to be supplementary because together they have to total 180 degrees because that's what a line would total. So that's what I went with, So I stated it as two angles are a linear pair if and only if they are adjacent angles that are supplementary. So there's two conditions to be a linear pair. So I had to make sure that my hypothesis being a linear pair and my conclusion would be adjacent angles that are supplementary. So um, if I would break this down into conditional statements, I would, in its converse, I would be able to produce two true if-then statements, and therefore that makes it a true biconditional, which makes this a good definition. For the third task in the first portfolio, you're given this figure here. You're being told that line AD, line BE, line CG, and ray OF intersect at point O. It's important to know that because, you know that AD is a straight line. So, the angles that would make up AOD, whichever way you're looking at it, should total 180. And that's important because if I don't have that it's forming a straight line, then I may not be able to assume that. Same thing with line BE and CG. OF is, on the other hand, a ray, and therefore not necessarily, having an opposite ray along with it that would form a straight line along with OF. And we're given some of the measurements in the figure. We're also given some markings. The two in red is particularly important. So they want us to find the measurement of all these angles and then provide some justification as to how we decided that that was the case. Well, when I go through a problem like this, I start marking things up, as well. And students who don't do that often make the problems like this much more difficult than they have to be. Now, I'm given a couple of measurements, although one's kind of hidden. I know I know the one angle is 52 degrees. I can see that it's BOC. But I can look at COD. I know it's a right angle because I see the right angle mark in there. So there's 90 degrees there. And I know that the three angles, COD, BOC, and BOA, would together be 180 degrees. And BOA is the other name for angle 1. So I know that angle 1, 52 degrees, and 90 degrees should total 180. So you're seeing all these marks come up at once. Or I could just look at the fact that, since that's the case, that angle AOC has to be 90 degrees as well, which makes AOB or angle 1 and BOC, the 52 degree angle, complementary. The measurement of angle 2 is, now I'm using the fact that we've discussed vertical angles, although we have not proven the theorem yet, but we've more or less seen that vertical angles are congruent to each other. And that's mostly because of the fact that, they form a linear pair with the same angle. In this case here, angle 2 and angle COD are each a linear pair to the angle AOC. AOC being 90 degrees. So if it's a linear pair with that, it has to total 90 degrees. And so that's kind of like an informal proof of the vertical angle theorem. And since angle 3 is a vertical angle with angle 1, it's also going to be congruent and be 38 degrees as well. Angle GOE would be 52 degrees because it's a vertical angle with a 52 degree angle, a BOC. Angles 4 and 5 make up angle GOE, and each one of them are congruent to each other. So they have to be two equal angles that make up 52 degrees, which makes each one of them 26 degrees. And then, so that's the explanations you're seeing down there. But marking up the figure certainly does aid one with that. So you have to make sure that you're doing that consistently, so that you can, justify the answers you're doing. If you can't justify them, then, the premise you're going under, it may not be able to be stated because you're just stating it because it would make their life easier if it just worked that way. Until you can verify it actually does work that way, you really shouldn't be making any kind of statements like that. So that was bring us to the end of the first one. Unit 3, Portfolio 2. Again, you're given a statement here. Statements with the same length are congruent. Write the type of statement based on the statement above. So a conditional statement for this original statement. Again, I want to be careful that I'm, creating the if-then statement right. I don't want to create any ifs that end up being, that is clearly, false. So this one's a little more straightforward. I wrote if segments have the same length, then they are congruent. And then the converse, of course, would be if segments are congruent, then they have the same lengths. The inverse would be if segments do not have the same lengths, then they are not congruent. And if segments are not congruent, then they do not have the same lengths. When I look at the if statements, can segments have the same lengths? Yep. Can segments be congruent? Yep. Can segments not have the same lengths? Yep. And can segments not be congruent? Yeah. So each one of those if statements can be true. Whereas like in the first instance I gave in the first example for task 1 of the previous one, the ones that were written in green, I couldn't, some of those if statements just didn't make sense. If January is not a month, then well, what is it? It has to be. Um, so these are the statements, and so we're going to go through the same steps we did for that other question I just referred to. Based on the response, what are the truth values? If segments are, this one's kind of straightforward and makes sense because remember, this is the definition of being congruent, for congruent segments to be exact. So you find that each one of these statements is true. So basically, if we write a biconditional statement, I would say segments have the same length if and only if they are congruent. And is this biconditional true? Well, since I go back up to the conditional statement in the converse, conditional statement in the converse, and since both of those were true, and those are the two statements that actually make up this biconditional statement, this by default also has to be true. So yes, it is a true biconditional statement, which in turn makes it a good definition. It better be, because that essentially is the definition of, congruent segments. So it better be a good definition because that's what we use for our definition. Now here, again, we're trying to get used to starting to deal with proofs. And one of the things you have to get used to doing when you're doing a proof is not only doing the correct steps, but making sure that you're verifying them to be correct by stating a property, a theorem, a postulate, a definition, something along those lines that allows you to do that step. And sometimes when you're asked to do these, oftentimes you're asked to fill in the reasons. Every once in a while, like in D here, you're asked to fill in a blank and you have to try to think, okay, what's the intermediate step here? But in this instance, when I look at this, I'm starting with 2c squared equals 2bc plus 2a, and that's given. Okay, and because that was stated word for word, phrase for phrase above here. I would not naturally assume such a thing unless I was given it. So the next thing that happens in B is that, well, 2c squared became 4c squared, 2bc became 4, and ac over 2 just became ac. So I have to think, what happened here? What went on from step A to step B to get to, the statement I have in B? Well, for me to be able to do that, I had to multiply both sides by 2. So I multiplied both sides by 2, and I also have to remember that since there were two terms over here originally, both of them got multiplied by 2. So we have another property for that. That's why it's mentioning two blanks, because there's two properties at work here. The property that says we're allowed to multiply both sides of an equation by the same value is the multiplication property of equality. And of course, the law that says that if I multiply a sum by a constant, then each term of that sum gets multiplied by that constant. That's the distributive property. Now in C, I'm looking again. I looked again. What happened when I went from B to C as far as the steps go? Well, on the left-hand side, I went from a C squared down to a C. On the right-hand side, both terms originally had a C being multiplied in there. That's because I have letters next to each other, it's multiplication. And now those C's are gone. So what would cause that to happen? And notice it also says distributive property. That could also help you with like the previous step and say, oh yeah, because you're dividing, because in this case here you're doing something to those same two terms over there. So here, for each one of those multiplications of C to go away, I had to divide by C. If you want to say multiplication property of equality too and say, well, I multiplied by 1 over C, that's also correct. Because remember, in algebra, multiplication and division have the same precedence in the order of operation because they're considered basically the same thing. Multiplying by, 1/2 is the same thing as dividing by 2. They do the same thing, so so we consider multiplication and division to be essentially the same operation. So, but since we see here that we did divide, I said division property of equality. If you want to say multiplication property, that's fine. But that would usually require more of an explanation. Say I multiplied by a reciprocal or something like that. So now, as you can see here, in part D, we don't have the next step. But the reason for what we're going to get there should be the result of me taking what I had in C and applying the subtraction property. Well, the subtraction property says I'm allowed to subtract the same value from both sides. Okay. And I also want to take a look and see, well, where am I going to end up here? I want to end up down here. And I can see there's a subtraction involved. I said, well, how would I get there? Well, if I would subtract A from both sides, I could see myself getting there because I can see I have 4C minus A on the left equaling 4B on the right. So, so if I'm going to subtract anything to move towards what I have written in E, then I'm going to be subtracting A from both sides. So I'm going to say I end up with 4C minus A equals 4B. Now, usually something that we don't always do, we're going to use another property here because we notice here that the 4C minus A is on the left, the 4B is on the right. We just usually take it for granted. Like I could just switch that around automatically, but that's a property as well. I mean, you'll see a lot of proofs don't usually state it. I mean, if I say x equals 2 and 2 equals x, that's saying the same thing. But it is because of a particular property, which allows us to make that reversal. So in this case, they're having you name it. It's the symmetric property of equality, which some students for some reason get mixed up with the reflexive property. Just be careful about that. But those are the steps that justify each step we made here. And you were doing that all along whenever you were doing algebra. That's why some things you did were legal, some things were not. And if you were trying to do something illegal, you got a wrong answer. Because each of the legal things meant that you were applying a property or a theorem or a rule or a definition correctly. And when you weren't, that's when you made your errors. So here it says solve for x and justify each step. So when I see here is I see angle EPG, the big angle, and I do see ray F also intersecting at P, which means I cannot say angle P here because I have actually 3 angles that have a vertex at P. So if I just hold up and said angle P, it isn't going to work. So anytime and I notice I'm given measurements of the angles EPF and FPG as being 4x plus 2 and 6x minus 10 respectively. So when I say solve for x, that's because I'm going to be able to write an equation from this, but it's based off of me knowing a relationship between these angles. We discussed several of those relationships, through Unit 2 and through Unit 3. But some students have to make the mistake they think that every time you get a problem like this, you're going to set it up exactly the same way, and that's not true. Um, Here, a key word for us is the word bisect. That defines a very particular relationship between angles EPF and FPG, because those are the angles that are formed when PF bisected EPG. And essentially, for me to bisect an angle, that means that the result has to be two smaller angles that are both equal in measurement. So I know that angle EPF is congruent to angle FPG, which means that their measurements are equal to each other. And since 4x plus 2 and 6x minus 10 were being given as the measurements for those two, I would then substitute those in for the measurements. So there's my equation that I'm asked to solve. And now I'm just going to solve it. So I subtract 6x from both sides. I like putting my x's on the left all the time, whichever way you want to do it. I then subtract 2 from both sides. Now again, I was able to subtract 6x from both sides because of the subtraction property of equality, and I was able to subtract 2 from both sides because of the subtraction property of equality. Then I divide both sides by -2 by the division property of equality, and I get x equals 6. So I didn't write out the wording for it, but the whole thing is, as you go through and if you're doing correct algebraic steps, you should be able to name a property that justifies how you got there. And if you can't, that means that the step you might be doing is either being applied wrong or shouldn't be done at all. So sorry for all the jumping around, but the first time I had tried to do this recording for this slide, I had to, I noticed I had to use my pen a good bit, and I wasn't able to because I didn't have this going on the right screen. So I'm going to redo this part. And I also noticed in the next slide there was some drawings not showing up, so I had to make those happen. So, but basically here we're going to do a proof of what's going on here. So we're given that angles 2 and 3 are vertical angles, angles 1 and 2 are complementary, and angles 3 and 4 are complementary. So, the phrases, in this case, vertical angles, complementary, they mean something to us. But also we need to keep in mind that these are the things that were given. These are assumed to be true. And since they're assumed true, we take them as being true. Whereas this, next to the word prove, means that, we have to verify this. It cannot be assumed to be true. I'm not going to state, the very last statement of my proof should say that it should conclude with angles 5 and angle 6 being congruent. I am certainly not going to say at the end it's a given statement. It isn't. This is what I'm looking to show. So, that's the first mistake a lot of students make, is that they'll say that the last statement's given. Well, the last statement of the proof should never be given, because if it were given, you wouldn't be proving anything, because we already assume it to be true. So we want to be able to take the information that we have and be able to come up with saying that angles 5 and 6 are congruent to each other. So in this case here, we start with a couple of things. This is coming from the fact that the vertical angle theorem. Since I know that they're congruent to each other, that was given, and I know that vertical angles are congruent, I know that angle 2 is congruent to angle 3. And both of these are coming from the fact that, by the definition of complementary. Yeah, my writing's a little bit off here. So I know that angles 1 and 2 total 90 degrees, angles 3 and 4 total 90 degrees. Okay, so now I can make the statement that the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3 plus the measurement of angle 4. And it's you could either say it's from the transitive property, or I could say that it is substitution. In many cases, one can act as the other. Because I could look at it as me saying, okay, well, both of these are equal to the same thing, therefore they're equal to each other. That's what the transitive property says. And essentially the transitive property is often proven using the substitution property. Whereas I could say, well, I could also put it in terms of the fact that, oh, I didn't want to erase it all. Oh, I hate when that happens. I forget it's all or nothing on this one. So I don't want it that big. Yikes. Let's erase that again. So there's a vertical angle theorem. Definition of complementary. As I said, I could say transitive or substitution. And either would be correct. Because I said that I could look at substitution and say, well, since 90 equals this, then I can replace 90 up here with that right-hand side, and that's how I get that equation. So both are legitimate to be used in this situation. So next, what I do is I see like, okay, well, you know, I went from saying measure of angle 3 here to the measure of angle 2 here. Well, I knew that angle 1 and 2 are congruent. But by the definition of congruent, I know that the measurements have to equal each other, and then I did a substitution. That should be really an and substitution here. So, because I applied both rules. I used the definition of congruent to say I had equal measures. I just substitute one equal measure in for another. And then what you see here is that, well, then on this last line, I subtracted the measurement of angle 2 from both sides to get this, and then I automatically conclude that they're congruent. So here, I use the subtraction property. And the definition of congruent again. I'm not done yet. I've proven 1's congruent to 4, but that doesn't help me figure out that angle 5 and angle 6 are congruent, so I need to keep going. I can see that angles 1 and 5 and 4 and 6 are they're linear pairs. And I know that linear pairs are supplementary. So here I could say linear pairs are supplementary. Now what I have here, I have angle 5 being supplementary with angle 1 and angle 6 being supplementary with angle 4. And since angles 1 and 4 are congruent, I have angles that are supplementary to congruent angles. And if I have angles that are supplementary to congruent angles, they themselves are congruent. And that's a theorem. So that's my statement that lets me say that angles 5 and 6 are congruent, and therefore my proof is now done. So I'm not going to say the word prove here as my reasoning for making this happen. It is actually the theorem that says angles that are supplementary to congruent angles are congruent themselves. So, and the last one here. You're asked to prove or disprove. Now, when you're trying to prove, you know, as we've seen in the past, we're trying to show that, you know, we use a lot of variables and things like that because we're trying to show that, you know, it's the values of those variables does not matter. It works for any circumstance that this is occurring in. So to disprove something means all I have to do is show one counterexample that, you know, basically meets all the original conditions, but doesn't, you know, have the same, doesn't conclude the same way. So for this one here, we have 3 conditions that are given that we're assuming to be true. that APB and CPD are vertical angles, APB and APE are complementary, and CPD and CPF are complementary. This is saying, if this is a true statement, that means that automatically, as a result, APE and CPF, those angles have to be vertical angles. And the thing is, when people do this, they often draw the figure looking like this. And I can see, I mean, I see that angle APB, right here, and angle CPD right here. They're vertical angles. I drew them to be vertical angles. And they're also going to be congruent as a result. Angle APB and APE are complementary. Again, here's AP and AP, yeah, so APB and APE are complementary, so I know that I have a right angle down here. And that CPD and CPF are congruent, or complementary, so again, I see this right angle here. And I can use the fact that angles complementary to congruent angles are also congruent, just like there's that rule that fits with complementary rather than supplementary. And I can see here that when I have it set up like this, I can see that APE, this one I just drew with the double arc, and this one here are vertical angles. So everyone thinks, well, that I just proved it true. And, because you came up with a figure that works does not mean it's necessarily true. You would have to somehow verify that no matter how you rearrange this, it would work all the time. However, if I draw it this way, see here, I assumed, when I drew this, when we set this up, that that essentially APB and APE being complementary, that basically I'm kind of like splitting the angles. Whereas here, when I look at the angles, I still have APB, which is this angle right here, and CPD being this angle right here. I'm still showing them as vertical angles. That's still true. I have these two being right angles, which means that these are congruent to this. But you can see it fits all the conditions. Okay, it fits every condition here. I just have basically E and B in different, E in a slightly different position, as well as F. But I can see this angle and this angle, the two angles I'm talking about, APE and CPF, they are clearly not vertical angles. They do not form basically a set of two intersecting lines. So I have found a contradiction. I found one instance, and that's all I need, just one instance where all three conditions are met, but the conclusion is false. And because of that, I have just disproven that statement. So as I said, disproving is a lot easier. All you do is find one example that doesn't work, and you got it. That can be hard to find sometimes. You have to sometimes kind of be creative in how you do it, but it can be done. So. And that's kind of just rehashing what I just said. Okay. If you have any questions with either of these portfolios, please make sure to get in touch with me, and we can go through it in more detail. But until I see you all in live lesson, or if I get the chance to speak to you on the phone, I'll see you around. Have a good day, everybody.